we present Shared Modular Policy, a method for learning a single controller for a wide variety of robot morphologies, which can then generalize to unseen robot shapes at test time without any further training. So deep learning has been successful in solving a number of challenging tasks in many fields. The key success of deep learning does not lie in training these giant models, but in how well the pre-trained representation transfers to downstream tasks. For example, in computer vision, once I have pre-trained a network, I can take these embeddings to solve detection, segmentation, boundary, video, and so many more. So this success is not just limited to computer vision, but also in speech and language. In fact, it works so well in domains with passive data that today we can even follow a general recipe for solving new tasks. Step 1, we just download a pre-trained model, for instance, ResNet in vision, bird in language. Step 2, we can label some new data for the task we want to solve. And then we just fine-tune the last layer. And guess what? More often than not, this works pretty well and we can declare victory. So the question we ask is how can we translate the same success of transfer learning to robots? Well, it's very challenging because every robot is different. In fact, every robot has different shape and different morphology. For instance, what does it even mean for me to pre-train a controller for this NASA dexterous manipulator? Nobody even has this robot to train a controller for it. So deep reinforcement learning provides a nice formalism for robotic control, and it has been successful in many tasks. However, the catch is, for each task, a separate new policy is trained for each robot. But how well does it generalize? In fact, reinforcement learning is already very hard to tune at training time. So even if we can train it, the controller does not generalize to even minor changes in shape. For example, if we remove only the feet of walker, it completely fails. Can we address this problem on training on multiple robots? Yes, so prior works have tried it, but the robots they train are very similar to each other. Here on the left are robotic arms that only vary slightly in the number of motors. And on the right, they train on 2 legs, 4 legs, 6 legs, and test on other number of legs. These approaches are very limited in the sense that the agent topology is the same, and it only generalizes to linear topology. So can we train a single policy for robots with very different topology? For instance, how do you train a single policy that works on both walker and humanoid? So in today's talk, I'll talk about our approach that trains a single policy not only for one robot, 2 robots, but for a wide variety of different robots. In fact, after we train it for these robots, our approach can also zero-shot generalize to new robots without fine-tuning. But this problem is very challenging. First, we have different number of input limbs and different action space. Second, these robots are so diverse that the policy needs to model different gates at the same time. So before we go into the solution, we should wonder why should it even be possible to do this kind of problem? Is there any evidence in nature that we can find shared locomotive patterns across different animals? Well, in fact, there's a work in biomechanics that animals that have obviously different shapes like cockroach, crab, human, dogs actually share the same spectrum of forces acting on the ground for locomotion. Similarly, we also have evidence from precocial animals that can walk as soon as they're born. So they're born with this pre-trained innate controllers, which might be a suggestion that it might be possible to design a general-purpose pre-training controller that can transfer to new shapes. So in today's talk, we'll talk about how to approach this kind of problem. But before we go into the method, let me show you a teaser of the results. Here we show a wide variety of agents that can be controlled by only one single policy using our method. As you can see, even though the policy is shared across different kinds of robots, different behaviors can still be captured at the same time. So how do we even train such a policy? We take inspiration from the recent work on dynamic graph neural networks that exploit modularity at both the level of software and hardware. Specifically, we train a policy for each motor instead of the entire agent, and we share it for all the motors. To start, we train all the agents at the same time. For each agent, we consider its morphological structure in terms of the limbs that make up the agent, which in this visualization is a side view of a hopper. The shared modular policy operates on each node and predicts the torque value for each limb. Our objective is then to learn a single policy pi that controls one limb at a time and share it across all the limbs of the agent and across all the limbs of all other agents. But how do we use the same policy for different agents if they have different number of limbs? Well, it's very simple. Since the policy acts on each node individually, we may just as well use the same policy for a different agent and apply it to each motor directly. Take the example here, where we have hopper and walker, which have different shape and different number of motors. We simply apply the same network at each motor location. But does it work just like that? Well, actually, no. The walker immediately falls after reset. So what's wrong? The key observation here is that there's no global coordination because with a naive setup, the policy acts on each node independently. For example, it's impossible for the leg to decide whether to move forward or backward without knowing the overall pose of the robot. Therefore, in addition to the state input, we condition the policy on the message vector. This message vector X is passed in here by the neighboring node. Also, the network outputs a different message vector X prime and passes to the next neighbor. Now the policy is fully modular in the sense that it's just like Lego blocks. Well, for example, if we have an agent like this on the right, we simply copy the same policy 3 times for each of the limbs. Then the 3 networks communicate with each other through messages. Furthermore, if we have trained a modular policy on a robot like this on the left, say we're given a new robot at test time on the right, what do? We simply copy the modular policy and paste it to the desired location again and again. Now the question becomes, how do we pass messages if we want to achieve kind of global coordination on the left? A natural scheme is either from leaves to root or from root to leaves. However, a major limitation of one-way message passing is that it can now represent multiple gates because not every node can receive complete global information. In the case that where we train walkers with 1 leg and 2 legs together, the model learns the hopping gait earlier in the training. Note that the 2-leg agents can now alternate both legs. Later in the training, the model switches to the walking gait, where the 2-leg agents start to walk, but the 1-leg agent stops hopping, as the model can now represent 2 gaits at the same time. So to encourage global coordination and the emergence of centralized control, we propose to pass messages both ways, first bottom-up, then top-down. So what's inside of this shared modular policy pi? It has 2 internal components, a bottom-up module and a top-down module, which are 2 fully connected neural networks. The bottom-up module takes as input the limb's local states and the messages it receives from its children. It then generates a message and passes to its parent. The top-down module reuses the same message and also takes as input another message from the parent. It then generates the predicted action for this node and different messages that pass to its children. Here's one example. We first start from the leaf node. Each node takes its own local states as input and pass messages upward using the shared bottom-up module. After the root node receives the messages from the children, sequentially from top to down, each node predicts its action and generates messages for its children using the shared top-down module. We now show the results. So here are different variants of 2D humanoid. Our model is simultaneously trained on all of them. Although they have different number of limbs, some even have only 1 leg. The model works decently well on all of them. The 1-leg agents can hop and the 2-leg agents can walk. And here are the results by training the model simultaneously on different variants of walker and hopper. Similarly, the model obtains remarkable performance across all of them. And these are the results from cheetah and its variants. The agents have different number of legs and thus have different behaviors. We take notice of these 3. As you can see, they apparently have different shapes. So this single policy adapts to 3 different gaits that best suited for them. But can our model zero-shot generalize to unseen agents? Well, the answer is yes. We first test on a set of held-out agents. These agents are from a similar distribution of the training agents. but the model has never seen them during training. So, but this is not interesting enough. What about agents that are very different from the ones that the model has already seen during training? It turns out the model can also generalize to those. These are the monstrous or weird-looking agents that the model has never seen before. As you can see, the model can capture locomotive patterns that never sees during training. Although they don't excel, it still tries to maintain balance, and these are all coming from a single model. This is a hypervariant that has only one that has actual limb. Note that because the agent is too high, the model can even figure out the agent better moves by flipping instead of hopping. Yet, there isn't a single agent that does flipping during training. This is a 2D humanoid with very heavy arms. The model also keeps balance really well. And this is another humanoid with no arms but 4 legs. Although there isn't a single agent during training that has 4 legs, the model can still figure out how to control such an agent at test time. Well, this works pretty well, but what if we further add objects to the robots? Can the policy still capture the new dynamics introduced by these objects? The answer is yes. Note that there isn't object at training time. Although they don't excel in moving forward, the policy can still maintain balance and the posture. This is encouraging, since the object introduced have new dynamics, and furthermore, the policy is only trained on standard cheetahs without any object. Take notice of this one, where the ball rolls to different locations during the episode. But the model still figures out how to control the only 2 motors properly to keep balance. But there are still some failure examples. If we make a giant version of Hopper and humanoid, the muscle strength is simply not enough to carry the weight. And if we also remove the legs of humanoid, it cannot move at all. So introduce this 2-way message passing scheme, but does the global coordination really emerge from this? To investigate this, we use t-SNE to plot the outgoing message from the root node during an episode, where the x-axis is the episode time step, and the y-axis is the t-SNE projection. We visualize both the walker and hopper environment. When the training starts, the t-SNE values are close to 0. In the middle of the training, we can see some patterns start to emerge. But in the end, we can see that curves vary with consistent patterns across an episode. With the walker, we can see that torso message exhibited 2 different peaks, corresponding to 2 different poses of the agent. While for the hopper, we find that there are 3 peaks, corresponding to 3 unique poses. And this is a clear indicator that there is indeed global coordination emerged from this both-way message passing. So in summary, we introduced shared modular policy, a method for learning a single policy on a wide variety of diverse robots. The policy is modular and acts on each motor instead of the entire robot. It passes messages first bottom-up, then top-down, and centralized control will emerge through this both-way message passing scheme, allowing the policy to model many different behaviors across many different agents. Furthermore, we believe this is an early step towards learning general-purpose pretrained controllers, which is a very difficult problem, as we showed. And what we achieve is a model that can achieve state-of-the-art performance on all the training agents using a single policy. And it can also zero-shot generalize to unsee robot shapes without any fine-tuning. So it's very encouraging. Well, so this is a super early results, but what lies ahead is very promising, and there's still a long way to go. Thank you.